the Pythagorean theorem. So we have just 3 vocabulary for this lesson, but it's a very important lesson. A lot of different types of math are built on the Pythagorean theorem. Okay, so the first 2 vocabulary terms are from right triangles. So if you have your right triangle, it'll look something like that. Okay, the hypotenuse is going to be the longest side. So in this case, this is going to be the hypotenuse. All right, and the other 2 sides are going to be what's called the legs of the triangle. Okay, they kind of hold up the hypotenuse. That can help you remember which is which. The hypotenuse is, like I said, the longest side. It is also usually referred to as c. That's the variable we use for the hypotenuse, for the length of the hypotenuse. And then usually for the legs we use a and b. Okay, doesn't matter which is which, but c is always the hypotenuse. Okay. Now the Pythagorean theorem is a rule, and basically it says that for any right triangle, okay, any 90-degree triangle, the sum of the square of the legs, so our legs are A and B, okay, and the sum of the square of those 2, so A squared plus B squared, and sum is meaning addition, is equal to the square of the hypotenuse. Okay, here's our hypotenuse, and that would be c squared. Okay, and we have a little proof for this. All right, you can see this diagram. So inside is our triangle, our right triangle, and we're given our values, our 3 values. Okay, so this leg is 3, and a square, right? If we make a square with side length, this side, this leg, okay, and then we put a square off of it, it's going to equal 3 squared. Right? 3 times 3, 3 times 3 is going to be 9. Okay, same thing for this one. 4 times 4, 16. So these squares represent the squared values of these 2 legs. Okay, and then this represents the squared value of the hypotenuse. Okay, we have a 5 by 5 square. So if I add up my squares for my legs, so 9 plus 16, 9 plus 16 equals 25, that is 5 squared. Okay, so that's my proof. And this works for any values, but a lot of the times you're not going to have nice values like this. This is what's called a special triangle, okay, because this is an integer, this is an integer, and this is an integer. Okay, it's called a 3, 4, 5 triangle. There are also special triangles that are multiples of these. So we have 3, 4, 5. We could have 6, 8, 10. All right, those are also going to be whole values, right? Whole integers. There's not going to be decimals. Most often, the triangles you'll get would be like, 4, 6, and then you'd have 4 squared plus 6 squared, and it would not end up as a regular integer. Okay, so that's what makes these triangles special. All right, concept 1 is finding the length of the hypotenuse. Okay, and to do that, you're basically just going to be plugging it in to the Pythagorean theorem. So a squared plus b squared equals c squared. And if we had, 3, 4, and 5, or say this value was, we can go 9 and then 12. And if we didn't know what this one was, we'd just plug it in. Right? So 9 squared plus 12 squared equals c squared. 9 times 9 is 81. 12 times 12 is 144. And this is where it helps to have those perfect squares memorized. Right? So you can remember that 9 times 9 is 81 and 12 times 12 is 144. Okay, add these two together. Should be 225. Oh, it's a terrible 5. And that is equal to c squared, right? So we've got c squared, but what we want is just c. Okay? So to figure that out, we are going to take the opposite of this square, which is the square root. Okay? So we're going to square root both sides of our equation. Because if you have a value squared inside of a square root, they just cancel each other out. So there's no more squared, there's no more square root. I'm left with just c. Okay, so c is equal to the square root of 225. Oh man, I'm struggling with 5s today. 225. Okay, and then that one, because it's over 144, I would say just plug that into your calculator and let that do the math for you. So we have 225 square root, and that's 15. Okay, so c is going to be equal to 15. And you're done. Okay, and that was a pretty nice one. We ended up with whole numbers. If we had used different values, we might end up with a really long decimal, a decimal that goes on forever. And in that case, you could just leave it as the square root of whatever that value is. But if it's a perfect square, you want to simplify it.